Alrighty, here we go with the Chapter 8 review. Number 1, the government claims that students earn a mean of $4,500 during their summer break from studies. A random sample of students gave a sample average of 39.75, and a 95% confidence interval was found to be 35.25 to 44.25. Which of the following is the correct interpretation of the 95% confidence level? So I'm not interpreting the interval. That's the we are 95% confidence sentence. I'm interpreting the level. What does that 95% actually mean? So what that means is, now what we would say is that if we repeat this study many, many times using the same method, same sample size, then 95% of the intervals would capture the true value. So we just got to see which one of these sentences sound that way. If the study were to be repeated many times, sounds good. There is a 95% probability that the true average is not 4,500. I don't even know what's going on with that sentence, but there's two things that are wrong there. So it's not a 95% probability. It's 95% of the intervals would capture the truth. So that's off the table. B, because our specific confidence interval does not contain the value 4,500, there is a 95% probability that the true average earning is not 4,500. That's kind of the same thing as part A was saying. So again, where it's not that there's a 95% chance that it's not in there. It's that we're 95% confident that the intervals created, there's 95% of the intervals created are capturing the truth. If we repeat our survey many times, then about 95% of all the confidence intervals will contain the value of 4,500. So it's not that it is, well, let's see, if we were to repeat many times, it's not, we're looking for the true value, okay? The 4,500 is what the government is claiming, but we don't know that the government is telling us the true value. So we don't know that the 4,500 is the true value. So we can't really say that that's what we're trying to capture. We're trying to capture the actual true value, not just the government claim. If we repeat our survey many times, then about 95% of our confidence intervals will contain the true value of the average earnings of students. That one sounds really great. There is a 95% probability, that's out, that the true average is between this and this. So again, it's not the 95% probability, it's that 95% of the intervals would capture the truth. So that's number 1. Number 2, the survey in the previous question was conducted by calling landline telephones, and those conducting the survey are concerned about the possibility of undercoverage, which is a type of bias, since some people do not own a phone or own only a cell phone. Which of the following is the best way for them to correct this source of bias? So if I change my confidence level, that's going to change my margin of error. Margin of error does not account for bias. So using a different confidence level is not going to happen, not going to help. Same thing with using a higher confidence level. Confidence intervals do not account for bias. Take a larger sample. If my sample is biased, then a larger sample isn't going to change the fact that it's still biased. So that's not it. Take a smaller sample. Well, that would be really bad, because then I would have variability and bias. So it looks like we need to just throw this sample out and start over, because confidence level and sample size do not account for bias. Okay, so throw out the sample and start over. All right, number 3. Peyton takes a simple random sample of 28 seniors at his school and finds that 20 of them are planning to participate in the school's annual Capture the Flag game. He wants to construct a confidence interval for P, the proportion of seniors who plan to participate in the game, but he realizes he hasn't met all of the conditions for constructing the interval. Which condition has he failed to meet? First thing, right off the bat, you guys. This is a confidence interval for proportions. It says it right there. So that means that central limit theorem is off the table immediately. That is for means problems only. So central limit theorem is gone, okay? N times p hat has to be greater than or equal to 10, all right? We need to check to see if that condition has been met. N is our sample size, that's 28. P hat is the proportion of success in the sample, so that would be 20 out of 28. That would be 20. That is greater than or equal to 10, so that one is perfectly fine, so I don't need to worry about that one. Let's check the other one. Now, if 20 of them say that they want to play, that means that there's 8 of them that say that they do not. So my success was 20, but that means my failure is 8. That is not greater than or equal to 10, and therefore we have a condition that has failed. This is a failed condition. D says that the population has to be normal. That is not true. The population does not have to be normal. That as long as our large count condition is good, then we don't care what the original population looks like. The sample is not representative of all seniors at the school. Well, if he took a simple random sample, then we can assume that it was a good simple random sample and that p hat is a good estimator of p, so that's not a good option either. So the answer here is C. Number 4. Which condition do we check to ensure that the sample statistic is a good estimate of the population parameter? So basically what this is asking is, which of these conditions is important for making sure that p hat estimates p and it's unbiased, basically. So which of the conditions do we check to make sure that we have an unbiased estimator of p? So remember our formula, p hat plus or minus the z star times the square root of p hat 1 minus p hat over n. And for this formula, there are 3 parts. The first one is the p hat. The second one is the z star. And the standard error is the third part. So, p hat is 1. Why do we check that first condition? To make sure that p hat is a good estimator of p. And that first condition that we talked about was the random condition. We check the random condition to ensure that p hat is a good estimation of p. Z star critical value, that's our normal condition. So z star, normal, that would be what we would check for the second one. 3, this is our standard error, and so our standard error is that we need the 10% condition to work. When we're doing proportions, the central limit theorem is never checked. That is only for means. Number 5. The Gallup poll plans to ask a random sample of adults whether they attended a religious service in the last 7 days. Conditions were checked and verified. The resulting 99% confidence interval was 0.42 plus or minus 0.01. What that means right there, you guys, is that p hat is 0.42. The margin of error is 0.01. So I know the actual p hat for this sample, and I know the actual margin of error for this sample. What was the sample size used to obtain the interval for the population proportion who would say that they attended a religious service? So I'm going to need to solve this formula. Margin of error, which I do know. I don't have to use the desired margin of error because I actually know the real margin of error, equals the z star critical value for 99% times the p hat 1 minus p hat divided by the sample size. So the only thing I don't know right now is the z star critical value for 99%. So I'm going to need to find that using my calculator's inverse norm function. If 99% is in the middle, that means I'm missing 1%. That means that there is 0.5% on this lower end here. That means the area of that is 0.005. So I'm going to go and use my inverse norm calculation. Second var's inverse norm. Area is 0.005. The mean is 0, and the standard deviation is 1. All right, and that's going to give me my z star critical value for 99%. When I find that, I find that the z-star critical value is 2.576. So now I can use that in this formula. So the margin of error is 0.01. The z-star critical value, 2.576. The square root of 0.42, the complement of that would be 0.58, divided by n, which is my sample size. This is now an algebra problem. If you guys are struggling with this, please be very, very careful with your algebra here. So make sure that you guys are ready for doing some algebra tomorrow. 2.576, I'm dividing by 2.576 on both sides. When I divide by 2.576, I get, sorry, I'm going to have to get this out of the way. I get 0.00388 equals the square root of, I'm going to go ahead and multiply these two numbers, 0.42 and 0.58, and that's 0.2436 divided by n. I need to square both sides. So next step, I'm going to square this side. I'm going to square this side. And I get, now you guys are going to get a scientific notation on your calculator. You need to be careful with this so that you don't drop that scientific notation, because it is not 1.505. It's 1.505 e to the negative fifth. And that is a very different number than 1.5. So make sure you guys are careful. Those numbers usually are going to be pretty small right there. And that's 0.2436 divided by n. And now I'm going to multiply both sides by n. And then I would divide by that scientific number. So my final answer is going to be 0.2436 divided by 1.505 e to the negative fifth. All right, so remember that you can get that little scientific e by using second and the comma button right above the 7, just like when you guys put in infinity in your normal CDF stuff. So you can put that into your calculator. So you just need to calculate 0.2436 divided by 1.505 e to the negative fifth, and that's going to be your sample size. When you get that answer, you're going to get something pretty close to 16,100 and something. This is the closest answer to that. Okay. Reason that it's slightly different is just round off error. We may have rounded slightly different than this particular problem. On these kind of problems, usually it's pretty clear. Just, I would say try to go 3 or 4 decimal points on these kind of problems. Okay? All right. Number 6. Number 6, it says, in January 2010, a Gallup poll asked a random sample of adults, in general, are you satisfied or dissatisfied with the way things are going in the United States at this time? In all, 256 said that they were satisfied, and the remaining 769 said they were not. Okay, be careful on this. 256 said they're satisfied. 769 said they are not satisfied. So we actually don't have the total sample size until we add those two things together. So it says, assuming all conditions for inference are met, we need to find the 90% confidence interval for the proportion of adults who are satisfied with how things are going, and then interpret it. Okay, so here's what we have. We have our success is 256. Our failure is 769. So that means our total sample size is 1,025. Okay, it's the total of the successes and failures. Okay, so we also need our z-star critical value for 90%. Okay, we're going to need our z-star critical value for 90%. Now remember, that's one way we have found several times. 1.645. And so we can go ahead and use that value. If you don't remember that number, that's okay. You can do the inverse norm trick. There's 5% over here, so that would be an area of 0.05. You can do that if you need to find the Z-star critical value, okay? Either way, whether you remember it or you just want to do inverse norm, either way, okay? Okay, the last thing we need here is just our p hat value, which is the successes over the total sample size, 256 over 1025, and that is 0.2498. So to find our actual interval, we're going to use the formula p hat plus or minus the Z-star critical value times the square root of p hat 1 minus p hat divided by the sample size. Our p hat value is 0.2498. Our Z-star critical value, 1.645. Square root of 0.2498. The complement of that would be, if I take 1 minus 0.2498, I get 0.7502. And then divided by n, our total sample size is that. At this point, you guys, it's just a plug and chug. We just got to simplify all of this. So I have my p hat plus or minus my Z-star critical value. And I'm going to go ahead and simplify all of this underneath the square root here. So when I do that, I'm going to get 0.01352. I'm going to go ahead and multiply that by the Z-star critical value. This is going to give me my margin of error. So the margin of error that we get here is 0.0222. So I take p hat, my 0.2498, and I'm going to subtract that margin of error. That's going to give me my low value. When I take that 0.2498 and I subtract the margin of error, I get a low value of 0.2276. And when I add the margin of error to the p hat, I get 0.272. And so what does this mean? We are 90% confident that the interval from 0.2276 to 0.272 captures the true proportion of adults who are satisfied with the U.S., basically. Just context of the problem there. Okay, so very important that you are able to plug in numbers and get that interval and then be able to interpret it. Okie doke. Moving on. Number 7. A manufacturer of flashlights wants to know how well one of their newer styles is selling in a chain of large home improvement stores. They select a simple random sample of 20 stores, record how many of the flashlights were sold in a 30-day period, and construct a 95% confidence interval for the mean number of flashlights sold. If instead of constructing a 95% confidence interval, the flashlight manufacturer constructed a 98% confidence interval, would the 98 interval be wider, narrower, or the same width as the 95? So when I increase, if I'm going from 95% to 98%, my interval is going to get wider. It's getting wider because I have more options to be right. I'm increasing my percent chance of being right, and a wider interval has more options in it. So that's why I am more confident. If instead of constructing a 95% confidence interval, the flashlight manufacturer constructed a 98% confidence interval, would the risk of being incorrect be larger or smaller? So with a 95% confidence interval, the risk of being wrong is 5%. With a 98% confidence interval, the risk of being wrong is just 2%. So, if I go from 95% confident to 98% confident, that means my risk of being wrong is going from 5% to 2%. So I have a smaller risk of being wrong. How would the width of the confidence interval change if the flashlight manufacturer took a larger sample but kept the same level of confidence? So I'm increasing my sample size. When I increase my sample size, that decreases variability. And the variability is measured by the margin of error. So if I increase my sample size, that decreases my variability, which means my margin of error would decrease. If the margin of error decreases, then that means the plus or minus goes down whenever I'm adding it to the p hat. So that means that my interval would get narrower. Alrighty. Awesome. Number 8. Number 8, find the Z-star critical value for an 89% confidence level. So these are just basic Z-star critical values using inverse norm. If I have 89% in the middle, that means that there is 11% left over. Half of it is going to be on the left, half of it's going to be on the right. Half of 11 is 5.5%. That means this lower area down here has an area of 0.055. I just need to find out what the Z-star critical value is. Inverse norm, area is 0.055. The mean is 0. Standard deviation is 1. I plug that into second vars, and my Z-star critical value for 89% is 1.598. Alrighty, Z-star critical value for 98.5%. So if I have 98.5% in the middle, that means that I have left over 1.5%. And that means that half of 1.5% is going to be on each side. So that is 0.75 of a percent. There's 0.75 of a percent on either side. So the area of this region here would be 0.0075. So I can do inverse norm, excuse me, inverse norm, area is 0.0075, the mean is 0, standard deviation is 1, and my Z-star critical value for a 98.5% confidence level would be second vars, inverse norm, 0.0075, 2.432. Awesome. Let's move on to number 10. All right, number 10, Corbin asked a random sample of 200 McKinney-Boyd students for their opinion about the Live Kind initiative. Using the results from the sample, the C% confidence interval for the proportion of all students who approve of this initiative is this right here, 0.864 to 0.936. Find the point estimate and the margin of error. So remember, point estimate is directly in the middle, okay? That's going to be your p hat is equal to, so to find that value, I just need to find the average of those two numbers, and that's going to be the middle of that interval. When I average those two numbers, I get a point estimate equal to 0.9. The margin of error is the distance out to either side, and so the margin of error would be 0.036. So I have my point estimate and I have my margin of error. Using the formula for margin of error and point estimate from part A, we need to find the z-star critical value. So remember, we have margin of error equals the z-star critical value times the square root of p hat 1 minus p hat divided by the sample size. The margin of error was actually 0.036. I don't know the z-star critical value because I don't know the level of confidence yet. That's what I'm trying to find. And then the square root of 0.9 times 0.1 divided by the sample size of 200, which we do know. I'm just going to do some calculations here. I'm going to go ahead and figure out what this is. 0.036 equals z-star. And the square root of 0.9 times 0.1 divided by 200 equals 0.0212. Alrighty, so I'm just going to rewrite this up here so I can show you guys what I'm doing. This is just rewritten. Didn't do any steps here. Okay, so now what I'm going to do is I'm going to divide by 0.0212 on both sides. And that gives me a z-star critical value that is equal to 1.698. 1.698. Now, that should look kind of familiar. That's pretty close to that 1.645 that we are familiar with. And so the z-star critical value is 1.698, which this shows is slightly bigger than the one we do know of 90%. So it would seem like my C percent confidence is going to be a little bit bigger than 90%. So to find out for sure, what I can do is if I have my normal distribution, C percent is in the middle. My z-star critical value is what the distance is from the middle out to either side. So that's my boundaries, but that hold in that C percent in the middle. So all I need to know is what area is that in the middle. If I know the lower boundary is negative 1.698, the upper boundary is 1.698, then I can use normal CDF here. Normal CDF of that lower boundary, negative 1.698, upper boundary, 1.698. The mean is 0, and the standard deviation is 1. When I solve for that, I get 0.91. That means that the percent confidence is 91% confident. So my C percent confidence here is 91%. So again, what we did, we found, because we had the interval, we knew what the point estimate was 0.9. We knew what the margin of error was, 0.036. We were able to solve for the z-star critical value, which we found was 1.698, and then that allowed us to find the area that was between the 1.698 on either side. And so that gave us the area in the middle, which is our C percent confidence. All right, and then for the bonus, which the bonus is important, I would definitely not skip the bonus. So, what are the 3 conditions that we use for constructing a confidence interval, and why do we check each one? So here's our formula again. I know I talked about this earlier in this video, but this is the formula, and each one of these parts has a different condition. The random condition is for the p hat. That ensures that p hat is an unbiased estimator of P. So that's why we check the random condition, to ensure that we have an unbiased estimator of P. The second part of the formula is the z-star critical value, and we check the normal condition for this, And just FYI, that's the large count condition for proportions. And for this normal condition, we check this to ensure that we can use a z-star critical value. As we just saw in the previous problem, we need to do normal CDFs and inverse norm calculations to get z-star critical values. Z-star critical values are based on a normal distribution. So this ensures z-star can be used because we have a normal distribution. So that's why we check that one. And then the third condition is one we've been checking for a really long time. It's the 10% condition. And we talked about this last week about why that's important. And this is to ensure our observations are independent. Remember, this is so we don't get little pockets of bias, okay? Ensure observations are independent and there is good variability in the sample. And that is why we check the 10% condition. Those are going to be important for you to know. So make sure that you know when or what each of those conditions are for. All right. Study hard. Good luck.